have already been addressed now by our colleagues, but yeah, we'll see.
Called AID. It's funded by Beaux-Arts, and you have the partner logos on the top of the screen here. And these will be the speakers today, and we're all up here on stage. And so I'll first give a short introduction on federated learning, explaining why federated learning can be useful. Then we'll have a talk from David on the architecture and when is federated learning useful for you, in which context. And then we'll have two presentations, more technical presentations, on what is a federated learning platform, and if you want to use it, what does this platform look like? Okay, so just a few slides, very general. So the first one here about training. So very often when I speak to people, they tell me, and that's the cartoon you see on the left side of the slide, that I very often hear, well, I don't need to train AI models, I just want to use them. And then I try to explain that, well, of course, for large language models, there are very few people training large language models in Europe. I think it's just Mistral who's still doing it. But there are many cases for language models and other models where you do have to do training if you want to achieve certain performance requirements, robustness requirements explainability requirements, and also work on the trade-offs, for example, between robustness and performance. Okay, so you do need to train models, and it can be fine-tuning, but also model distillation, where you take a model that's large and you reduce it, you cut out the parts that you don't need, and then you train it, you specialize it for your specific needs. So this is why I think more people will need to train AI models than they think, okay? So I think there's a real need for training and helping people learn how to train AI models. Second, data. Very often I hear, well, we don't have the data. Unfortunately, people who want to train models, we don't have the data. And I've been hearing this for years. And even recently at a large a European conference, I heard the organizers, the German organizers, saying, well, it seems to be that the big problem is that people don't have the data. Okay? So access to data is actually a key issue in Europe. And here are just a few, I would say, comments on data. So there are many large industrial companies in Europe that have large amounts of data, but they don't have the, I would say, the expertise to train the AI models. And I'm thinking of companies like Volkswagen, where they have lots of data, automotive, they have lots of data, but they're not the ones building these large language models, or they're collaborating. Also, there are many companies that you think they have data, and but actually it's their customers' data. It's not their data, so they can't use it for training. And I'm thinking of data centers or telecom operators. They're managing data, but it's not theirs, so you cannot use that data for training. So that's another issue. There's also the issue of data quality and variability that you need for training. You need highly trained, curated data to train a quality model. There's also the issue of regulation in Europe, which makes it a bit difficult to centralize data in clouds to do the training. So all this points to the fact that in Europe, data will be decentralized. And we won't have the hyperscalers like in the US that they collect the data centrally, and so they can train models on the data they have. In Europe, this won't happen. So last bullet point, in Europe, at least the European Commission has a view on federating infrastructure data. So they're working on really mechanisms for federation, and they call it multi-provider cloud edge continuum. And there are a number of initiatives like the IPCEI CIS. This is a large project of projects on cloud, the cloud edge continuum. It's a €3 billion public-private budget. The initiatives on data spaces. These data spaces are environments where you can access data and respect the rules. It's making it easy to access distributed data. And AI needs this. You will need to access distributed data. And so data spaces might be a key component for this. But again, this is ongoing. The Commission is pushing this. There's the recent, they're starting up the IPCEI AI. And again, there, it's a view of a federated infrastructure for AI processing. Same thing with the AI factories. So all this points to the fact that in Europe, data will be distributed. And so if you want to train your AI models on data, you will have to do it in a distributed manner. Okay? So my last slide is, so you need you need techniques for collaborative training, and federated learning is one technique. And the key idea here is that you will train local models where the data is, so with the data owners, and then you aggregate the models into a global model that's in general better, simply because it's been trained on a greater variety of data. Okay? And this is what we're going to explain, this technique of federated learning. And if you're interested, we have platforms, and we can, we will show this to you. And if you're interested in collaborating with us, don't hesitate to contact us. Okay.
Thank you, Philippe, for the nice introduction. I'm a research manager with Disternet, and we already heard from Philippe and also from my colleagues earlier today that everybody these days is probably using AI, maybe also training AI. And now we'll be talking a bit more in detail what federated learning is all about. And I will explain a little bit what are the benefits, not just for us as researchers, basically, also in the AD project, but also for end users. And also, as already pointed out also in the previous talks, since we're dealing here with machine learning, there are many of security and privacy attacks. And these also occur in federated learning. So I'll give you some pointers of what kind of attacks can happen. And that, of course, means that we have to take precautions when we put federated learning into practice, as you will see also in the presentations from my two colleagues later on. So let's say up to 2016, when federated learning was proposed by researchers at Google, the main paradigm was basically traditional machine learning, where you collect all your data on your own, let's say, desktop computer if you're a researcher like me, or maybe you're a big company, and then you collect all the data in your data center and you train your model. And if you're happy with the results, you deploy it for yourself or for your customers. Of course, if you're dealing with sensitive data like user information, personal identifiable information, there are, of course, various risks. So imagine, indeed, you're a company, you collect a lot of personal data, then, of course, your company, your databases become a vulnerable, let's say, a very interesting target for attackers. I mean, you get a lot of data. So this is a severe privacy risk. On the other hand, sometimes you're dealing with complex machine learning models like LLMs, and that means that you have to collect a lot of data, sometimes with permission of the user, sometimes you just collect data legally or illegally, but nonetheless, it means that sometimes you're dealing with large volumes of data, and especially in a context where you're dealing with data coming from sensors, think of Industry 4.0 applications, it means that you have to send data from a sensor to maybe through a gateway to a centralized backbone. And this might become very costly because you probably know if you're dealing with sensors, communication is much more costly in terms of energy compared to local computation. So let's say dealing with these high resource requirements might be an issue. And as I already explained, sometimes we're dealing with very sensitive data, health information and whatnot. And here in Europe, we have, of course, the GDPR. Nowadays, we also have the AI Act. So as a company, we have to be compliant with certain constraints. Also in the States, we have regulation in that space, for example, HIPAA. Now, another concern that I want to talk about today is if you're, let's say, sharing your data as an end user, then of course, you do not know what's going to be done with the data. Hopefully, you will have read the privacy and other form that you have to approve. And then hopefully, nobody will actually abuse your data for maybe secondary purposes that you're not aware of. But in essence, you're never sure 100% whether what's going to be done with your data, who's going to be able to access that data and whatnot. And actually, that's a real problem. I mean, people actually do, for example, upload sensitive data like health reports, their blood values and whatnot in ChatGPT to just analyze the reports. So this is, of course, a very, let's say, risky business. But on the other hand, it also shows that there's a need for having, let's say, AI applications that can handle and process sensitive information like health information, because people really want to make use of that information they collect themselves. And in fact, there was an article in the New York Times a couple of months ago that really showcased what are the possible risks of doing so. So that's to a certain extent where federated learning comes into place. I'm not quite sure how many of you have heard of federated learning. Maybe show a quick haze of at least a couple of them. Okay, so I'll give a high-level overview. I will not be going into the details of federated learning. It's an area that has been existing for about a decade, more or less. But the idea is that rather than you pushing the data to the model, you do it the other way around. You push the model to the data. So in principle, what you see here in this picture at the bottom left, that's the traditional way of working. So you collect all the data to a centralized place, and there you train a model. What federated learning does in general is you let each and every party train a model on their own local private data. And then each of these parties who is involved in federated learning will combine their models in a certain way so that the global model, after combining all these smaller models, that the global model, the shared model, is much more accurate. And this has, let's say, two advantages. First of all, if you do it like that, what happens is you don't share the raw data, but you share the model, the weights, or incremental updates. And this has, on the one hand, as a benefit that model updates are typically an order of magnitude, or if not more, smaller than the raw data that you would typically need to train your model. And on the other hand, because you do not share the raw data, there is inherently an improved notion of privacy. The assumption is indeed that the models updates themselves don't leak much. And this is, in fact, not really true, and I'll come back to that later on. But let's say in 2016, indeed, Google came with this approach of federated learning to show indeed that this technology works under certain assumptions. Maybe in a bit more detail, looking at the architecture, so inherently you're dealing with a distributed way of learning. Typically, I have maybe hundreds, if not thousands, of nodes contributing to this federation, learning the local model on their own private data. And then there is this one party, in this case the parameter server, that takes all these model updates and combines them and then shares the combined model back towards the client. So what you see here in the picture is in green a number of clients. They are depicted in green indeed. And this could be a simple sensor. This could be maybe a server. This could be maybe a hospital because of companies working together. This can be basically anything. And then the parameter server, they will bootstrap the whole process by creating a model, for example, a neural network, initialize the weights, and then share this model through all the clients, or maybe a subset of the clients, and then the clients start learning. That's where you have the local epochs. So after a couple of local epochs, the clients share their improved model again with parameter server. They will combine them in a certain way, for example, through averaging. And the updated model, the combined model, is then shared again with all the client nodes. And the process continues until the model converges to a certain level of accuracy. This is how it typically works. So of course, to actually make this possible, there are a variety of requirements. It basically means that, of course, your clients have to be able to learn a model, so there are some resource requirements from that point of view. But nowadays, even with smartwatches, they are powerful enough to train models. Even they have now dedicated hardware to make these computations much more efficient. And as with any typical distributed application, of course, you have to make sure that all this communication between the nodes has been properly secured. The parameter server, of course, has to combine all these model updates in a certain way. And of course, you could think of, let's just average them. That might work. But imagine a scenario where you have maybe a node with 10 times more data than other nodes, then you would assume that that party probably should have a bigger impact. So there are many different ways to create this combined model. I'll come back to that later on. And also what happens in practice, especially if you're dealing with sensors or mobile phones or whatnot, it could be that some of these devices get out of touch with the parameter server. So you have to be able to handle that. And typically what you do is, imagine you have like 1,000 nodes in the federation. You just say, in every round, I'll just take 10% or even less to do the training round. And if a device drops out, well, that's hopefully maybe by the next round, they will be present again. So that's just purely from a technical point of view. Of course, also from a non-functional requirements point of view, there are various requirements. I already talked about privacy as a key concern. But inherently with federation, of course, you assume that everybody is playing fair and correct in the sense that they all learn the same model and that they're using the proper data. And of course, in practice, if you're dealing with adversaries, this might not be the case. And other concerns that might happen is the fact that there's a lot of heterogeneity in the sense that sometimes you have clients which have a lot of resources or good communication bandwidth to do the federated learning. It could also be that these devices have heterogeneous data. And this is actually a very big challenge because in those scenarios, it might be that your model does not converge as quickly as you would have in a centralized manner. So I'll highlight a couple of benefits of federated learning. So inherently, like I talked already, like I already mentioned before, With federated learning, your raw data never leaves your device. So the idea is that this gives you better privacy. And the first application that was built like that is actually the Google keyboard. So if you have a virtual keyboard on your mobile phone, what it typically does, if you enter a couple of characters, it gives you the most likely word, or maybe the next word, and inherently there is a machine learning model behind it. And this was actually trained by Google through federated learning. And why was this important? Well, of course, you don't want Google to know everything that you type. So they had like a federated learning mechanism to learn which are the most likely next words and so on. So this is how, for example, Google doesn't get to know your passwords, for example. So in that sense, there is indeed an improved privacy. Also, like I already said before, because you're sharing model updates rather than the raw data, it gives you improved usage of your network capacity because the models are up to maybe 2 orders of magnitude smaller. Of course, you're not going to train large language models on your smartwatch, but if you're running an application for health monitoring, then this is actually indeed what you can expect. So as a benefit, your battery consumption of your smartwatch or maybe sensors in your company might run for much longer compared to when you would share all the data continuously with the backend. And then a third is basically better personalization. What you get with federated learning is the best of both worlds if you would compare that to centralized machine learning, because in that scenario, when you share all the data of all your users towards a centralized backbone and train a model there, then in the end, all the users would just get one single model. So it's a one-size-fits-all model. But with federated learning, of course, you not only learn from your own local data, but you learn also from many other nodes. And this might actually help to improve the behavior of your application through indeed learning from your own patterns and those of others. However, like I said before, there are various security and privacy threats. And as already Vera mentioned before, and I believe my colleague Tim as well, threat modeling is very important. With threat modeling, what you typically do is you model the assumptions about the adversary. What can he do? What does he know? What are their objectives? And with federated learning, you might have different kinds of adversaries. You might have those that are outside the federation, and they might just monitor the communication to see what kind of models are being shared. But you might have, let's say, worse scenarios where the adversary is actually within the federation. It could be that the parameter server is malicious, or maybe one or multiple nodes in the federation are malicious. So that's how we characterize different kinds of adversaries. So you might have, let's say, in a single attack where just one party is playing the game not fairly, but you might have also what we call a Sybil attack, where multiple parties collude to launch a stronger attack. And then we can even further characterize the behavior of the attacker by just looking whether they follow the protocol of federated learning. And this is a scenario that we call honest but curious. So what can happen there is that the adversary plays nice, they follow the protocol, but they try to learn more information that they typically would not have access to. I'll give an example later on. But a more malicious one would actually be able to deviate from the protocol. Let me give an example. I mentioned in the beginning that the parameter server would share the updated global models to all the clients. Well, imagine that he would share different versions of the model to different nodes. That would be a malicious parameter server. So here are two attacks, which I think already were mentioned by Vera, but now in a federated learning context. So remember, here we're dealing with learning models. So we're dealing with, let's say, corrupting the model, for example. So here in federated learning, you also have a risk of poisoning attacks, where indeed, for example, you can manipulate the training data, your own local training data. You might be able to fool a model like that. An alternative attack would be that you manipulate the model updates that you share to the parameter server. So indeed, you can have one or multiple parties that could launch a poisoning attack like that. And you can go even a step further and do a backdoor attack. And then the goal is to have, let's say, a model that seems to work fine under certain circumstances. But if the attacker can include a trigger, for example, a yellow pixel in top right corner, then this might trigger behavior that is desired by the adversary. So these are all possible with federated learning because it's typically a learning process. There's also another attack like inference attack. It's slightly different. It's not really an evasion attack, but what can happen with an inference attack in federated learning is that a party in the federation wants to learn data from another node. And for example, what you do is you might have records with 3 attributes, or let's say 5 attributes, and an adversary wants to know all these attributes. So what he does is he tries to create the same values for the attributes, but with a different label. And then in the next iteration round, of course, you have to improve your model. And that means that the victim would then have to provide more information to be able to distinguish between the 2 variations. And that's a way of how the adversary can learn those attributes. I'm not going into details, but these are kinds of attacks that need to be taken care of. So indeed, what we can learn from this is federated learning indeed can be used for security applications, but there are also various security and privacy threats in federated learning, hence the project on secure federated learning. And now my colleagues will talk about more with a concrete use case on federated learning for security, and then also how to actually further secure federated learning itself. Thank you.
Thank you. Nice. Yeah. Thank you, Davy. I'm Laurens Doge. I work for UGent and IMEC, mostly as a postdoc, and this is one of the projects that I'm currently involved in. I will be talking about the platform that we built and about a specific use case, namely network intrusion detection. So, of course, I think this is not news to anyone in this room, that cyber attacks keep on growing, and of course, everybody is connected. So it's self-evident that we need protective measures. Just a single slide on what an NIDS is, in case it's unfamiliar, because this is an AI day and not a pure security day. So typically, a network intrusion detection system sits behind a firewall and in close to your own LAN, and essentially inspects traffic. It inspects traffic that enters, that is allowed through the firewall, to see if there are malicious payloads or if anybody is trying to move through your network in an unauthorized way. Historically, there's 2 types. There's the signature-based systems, and then there's the anomaly-based systems. The anomaly-based systems are the machine learning ones. The signature-based systems, they still exist. They are operational, they are functional, but they have the limitation that signature databases just have to keep on growing, and attackers always find new ways to essentially invalidate them. So I will be focusing on the machine learning parts. That said, network traffic is a very good data set for federated learning because it's exceedingly heavy. Usually, if you have your traffic and you just capture all of it, it could be hundreds of gigabytes every single day. You do not want to send this to a central server. You can, of course, pre-process it, but still, it tends to amount to a large amount of data very quickly, and it's extremely sensitive. If I have a copy of your data on my local machine, I can just see everything that you did. So, of course, if there's a lot of encryption involved, I can't see the content, but I can still infer a lot of things what you do. So nobody really wants to share this data with third parties. Everybody wants to keep this data private and local. So it's an ideal candidate for federated learning. This project has been going on for quite a while. It's funded by BOSA directly. And in 2024, we had a working prototype where we had a central server, several clients, but we did run into some bottlenecks. So we had a server, and the server was specific enough in implementation because for the federation, it was responsible for setting the global strategy. So how are we going to recombine these weights? There's multiple ways to do this. There's a lot of academic research on this. And it's, of course, a responsibility of the federated learning server to do this. Of course, also, it's responsible for starting the server, aggregating the weights, and evaluating the global model. Because ultimately, if you have a federation of clients, they all contribute a part. They all contribute a partial model. But if it is centralized and aggregated, you still need sort of a holdout data set to validate if this global model is actually functional. If the recombination of the smaller models yields a working, well-functioning ML model. The issue that we had was that we put way too much stuff in the client. This was a demo in 2024, and the client was responsible for storage of the data and pre-processing. It had to define the model, which is also a limitation, so it was baked in. Because the only thing it really should do is it should train, validate, and evaluate. That's the only thing that the federation client should do. All the rest of the infrastructure, where the data is, how is it pre-processed, should be done in separate services. So that's what we set out to do. Also, the first implementation in 2024 was not cloud native at all, and it was quite brittle. So this is the current version. It's a microservice architecture now. It runs fully on Kubernetes. It's currently running in our data center in Ghent. And there's also, we are in talks to have it geographically distributed with colleagues at UCL. So it has gotten, in a way, more complicated, but easier to deploy. So we have shifted off all the essential services so that now those core concerns where the client is only doing the local training loop, it's no longer doing the pre-processing, it just gets the data. We also have some clever tricks to make sure that it doesn't have to, that we don't essentially waste bandwidth on data, because we had to disaggregate these, but we still try to have an efficient system overall. So this currently is what is deployed and is still growing. The thing that we focused most on was that we have full lifecycle management. So we have a federated learning system, and there's frameworks, open source frameworks that support this, but they really only just give you the bare bones training loops. They have a server component and a client component, but all the remainder of the services that you need to actually make this deployable are nowhere to be found. So we had to build them ourselves, and that's what we've done. We built in scalability on proven technologies. So the original prototype had some difficulty scaling to many clients. The current version, so long as you have a Kubernetes cluster that's large enough, you can just add clients as many as you want. Something that's from an academic standpoint very interesting is that we focus a lot on reproducibility. So we run experiments on this cluster for federated learning, but of course we also want to have a full track record. We want, in an ideal world, we really want to be able to have a single run and then reevaluate that single run and essentially get the same results. We also worked quite a bit on fault tolerance, so it's much more stable than it was in 2024. And for model support, we now support any kind of Keras or TensorFlow model, and it no longer has to be defined in advance. We just have a separate service for this. So any client in the federation, they have to agree what the model is going to look like, and then they can essentially store it with us, and they don't have to worry about it anymore. And in terms of data modality, we currently support structured data, mostly binary structured data. We like to use Parquet. But we're also expanding into images, which we've already done. And in 2026, we're also keep on working to include time series as well, because there's a lot of interesting time series data that we currently don't support. We do metric tracking, but for this, we just use weights and biases. If you're not using this and you're an academic researcher, please do. It's quite easy to set up and actually gives a lot of information, so you don't have to reinvent every single component. And then weight protection is something we're very actively working on in 2026 to make sure that we and our colleagues, we essentially integrate the findings that we have. On IMEC side, we focused mostly on the platform, on how to make it scalable, robust, and essentially a well-engineered product. But we, of course, need to include additional protections for the weights themselves. I have a live demo. I'll see if it works. Yes. Okay. Normally, in a few seconds, it should start. So this is actually running live in the data center. We have the central server, some clients set up. They are all talking to each other. Normally, in a few seconds, we should start to see them essentially kick into gear. And the important thing is, of course, and it's what my colleagues have said before, is that we don't share data. So all these clients, they act separately. So the only thing we're really sending are the weights. Oh, starting. Okay. It is kicking into gear. The way it's set up is it's a little complicated right now. So yes, essentially what we want to see is that the clients will start their own training loops, and the server will start receiving the weight updates. Normally, this demo should run in like 2 minutes flat. And we'll see that in the end, the final step is where the server will send an aggregated version of the model back to the clients for another training round. And then very much as a final step, I'll show a run that we've done over a longer time period and show the metrics in weights and bias. Okay, so now it is actually fully running. The clients are training, and probably in like a minute, we will have our final result. Maybe while that is running for another minute, I will talk a bit about the data sets that we use. We are mostly focused on network intrusion detection as a use case, but we're also doing malware detection, and we're also contributing back to open source. I still have a slide for this that's coming after demo. But essentially, thanks to BOSTA support, we are not only able to do federated learning as a platform, but we're also still able to contribute to open research, which of course we value a great deal. I will let it run, and perhaps I will come back, well, when it's fully finished. Well, if I have 40 seconds, then I suppose I can I can fill this time without. Yeah, I guess we're just going to come back to this. The live demo. Luckily, it is working, so I don't need the video. No, I don't need the video. Voilà. So this is something that we've also done as part of the project. We have been showing this at various stages of development at several conferences. So we attended CyberStack Europe in April in 2025, and we also were at B-Cyber also in 2025. And so this is our first public appearance for the ED project in 2026. Overall, there's quite a bit of interest in federated learning, so we're always happy to essentially share our research. And this part is the thing that I alluded to while waiting for the demo, is that we like to give back to the community. So as part of our research effort, we've done a lot of work on dataset cleanup as well, because I'm a machine learning researcher mostly. So we focus a lot on how to essentially up the quality of the available data. And this has actually been a very worthwhile effort, because together with my colleague Sami from UCL, we've been able to essentially clean up and reprocess or repurpose datasets that have by now garnered well over 200,000 downloads on Kaggle. So we mostly share our work, it's all open. And now that I'm quite finished, I think that the demo should also be done. We're still running. Guess we're still running. Okay. Voilà, completed. We're done. So of course this was a very, very quick demo. It's only 2 minutes. It's not an actual full run. It's just to show that the system is fully functional. We can actually have this end-to-end system where the clients send their updates, they get aggregated, and the entire system works. And just to show a run that's a lot longer, this was a run for like 100 epochs. It's way too long because the datasets that we used didn't really need this. But we essentially integrate all our metric tracking in weights and biases. So that's it from my end. If there are any questions regarding implementation details, feel free to come and find me. And I will give the word to Xavier.
Thank you.
Oh.
Voilà. Hello everyone, my name is Xavier Lesage. I am researcher in AI and cybersecurity. And yes, with the federated learning, it's very nice. It's possible to train an AI without sharing the sensitive data. And of course, there are a lot of interesting applications about that. For example, as explained by Lawrence, it's possible to train an AI for several security issues, but in collaboration with several hospitals, it's possible, for example, to train an AI for the breast cancer. So I have two questions. I would like to share this with you. In comparison with the classical learning, with the centralized learning, is better or not? There are a lot of papers about that, and on this slide, on this paper, you have a comparison between several kinds of learning, federated learning, distributed learning, and centralized learning. So in this case, in green, you can see here the result, the precision for the federated learning. I have the opportunity to do a lot of experimentation with several kinds of data sets, and some constatation with the federated learning is better, and sometimes we have a few % more. But I have a second question about the security. It's by definition a distributed architecture. So we have a lot of potential attacks, like explained by Davy. So we have inference attack from the model, from the data set to obtain the information, and we have the poisoning attack to the model, to the data set to make some perturbation in the training. So it's very, very important to secure this architecture. And for example, on this slide, it's possible to do an attack between the central server and the local server one. It's possible to change the value of the weight for this model. So, like explained by Davy, there are a lot of attacks, poisoning attack, backdoor attack, inference attack, and fortunately, we have for each kind of attack a countermeasure. I have no time to explain in detail, in deep, all defense techniques, but I would like to speak about the differential privacy and the homomorphic encryption with you to explain the context. For example, with the differential privacy, it's possible to add some noise into your architecture. On the left, you have a neuron, for example, and on the right, it's possible to add some noise, the Gaussian noise, to change the real value. You can see here the result with a real architecture is the information about the tensor, and you can see here the impact on this noise. Of course, if the noise is too important, there is an impact on the accuracy. So it's needed to identify what is the best trade-off between the security and the accuracy. It's a classical problem. Another solution consists to use the homomorphic encryption. It's a mathematical approach, very, very complex, but the idea consists to have the opportunity with this technique to do some operation, addition, multiplication on the encrypted data without decoding. So it's very nice. And here is an example. It's more simple. If I have two data, A and B, it's possible to encrypt this information, make several operations, addition, multiplication, and without knowing the value of A and B, make several operations, and in this case, obtain the result with a multiplication or an addition operation. It's based on private key, public key, and depending of the use case, dataset is relevant to select the best schema for the homomorphic operation. I have the opportunity to evaluate this mechanism, this countermeasure, with the real data from an hospital in Belgium for the breast cancer, with homomorphic encryption and without homomorphic encryption. And it's very nice. You can see here the result is very similar. So the impact is transparent. Of course, like Lawrence, for this experimentation, I have the opportunity to use Flower. Flower is a very nice framework to do the federated learning. And we have a demonstrator for the ED project based on Kubernetes, Flower, MQTT, and Vue.js. It's possible with this demonstrator to do several experimentation with a public data set, for example. And here is a first overview, a first print screen about the first step, about the transfer of key. We have the public key and the private key, so it's needed to share this key for this collaboration, this coalition. And for the last slide, you can see here an example of the training. We have several clients, in this case 3, and it's possible to start the first cycle, the first round, with the client 1 and 3, and probably after 1 minute, the client 2 will be available. And thanks to this collaboration, without transfer of sensitive data, it's possible to build a global model for this coalition. Voilà. Thank you for your attention. Voilà. If you have some questions, I can help you. Yes? It's not okay.
Thank you so much for your presentations. This is probably a question to any of you in the committee. Do you believe that for certain types of data, there needs to be a regulatory demand to use federated learning? Or would you say that realistically this will always be up to the vendors or up to the organizations?
Yeah. Okay. Yeah. The mic is working again. Thanks. I think it's going to be very difficult to regulate. As you already pointed out, sometimes regulation is always behind technology, basically. And I guess companies that especially focus on data, because if the value is in the data, then they, of course, are never willing to share their data. That's what we see, for example, in pharmacy. Of course, they have a lot of data, and they want to have solutions to build new medicines or whatnot, but they're not going to share their data. And indeed, there are solutions like federated learning, but that's not necessarily strictly necessary. For example, if you do federated homomorphic encryption in the cloud, that might also work. It just depends on the kind of threat knowledge you have. And in terms of regulation, what's the focus of the regulation? Because there is so much regulation out there. Do you focus on personal data, or is it something else? So
that's what I had in mind, indeed. If this is sensitive data, and right now the go-to practice is to build AI systems on sensitive data, for instance, collected from mobile phones, and that's allowed. But so you think that even if that would be a good goal, realistically, you don't think that will happen in the short term, that it will be regulated?
Well, legislation would work if they would be able to enforce it. And that, I guess, is always the biggest challenge. So you can make as many laws as you like. If you can't really enforce them, or you can't even figure out something went wrong. Yeah, so that's my personal take. Again, I'm not a lawyer, I'm a technology guy, so that's where I come from. Other questions? Or remarks? Or suggestions? Or is everybody thirsty or whatever? Or
No more questions? Okay, well, it's a wrap then. Thank you.
Thank you very much.
Thank you very much.